Hello everybody and welcome to Chapter 7. We're going to start Chapter 7 by talking about what a chemical equation is and how we can write them and how we can balance them and all that they can tell us, which actually is quite a bit. So the first question is, what does a chemical equation tell us? Think about that for a minute and look at the equation given, which actually relates to the lab that you just recently did, that you wrote up based on the reaction between magnesium and oxygen in the air. So this would be the chemical equation that represents that process. So just pause and take a look at that and tell me what you think you know based on what you see there. So as you can now see, there's quite a bit of information here. The reactants are the substances that we have before the reaction takes place, and they're written to the left of the arrow. Products are what we have when the reaction is complete. They're written to the right of the arrow. The arrow means any of these things: yields, produces, forms, makes, creates. So many verbs can be used in that spot. And states of matter are indicated with parentheses after the substance's formula. So S for solid, G for gas. There are two more. L is liquid, and AQ is dissolved in water. Technically, the word for that is aqueous, and that's why we use AQ. Now, equations need to be balanced. And we didn't actually do that on the previous screen, so we'll take care of that in a moment. Let me first ask, why must we balance equations? Well, if you think way back to something you might have heard of in the past, or if not, there is something called the law of conservation of matter, which basically says that in ordinary chemical and physical changes, matter is not created nor destroyed. The amount of atoms that you start with must be equal to the amount of atoms you end with. The amount of mass that you start with needs to be equal to the amount of mass you end with. Okay, and that's a sort of a fundamental law for the behavior of normal chemical processes. There are some situations where matter is lost or gained, but those are not chemical processes. Those are normally nuclear reactions. And we're not going to deal with those in this course. So here's the equation from the previous page. And you'll notice that the atoms on the left and the right are not equal. The magnesiums agree, but the oxygens do not. So when we have a situation like this, where the atoms are not the same on the left and the right, here's what we're going to do. We will think about it and look at the imbalance of atoms and add numbers to the left of each formula that are called coefficients that will reestablish the equality of atoms on the left and right side. Because there are two atoms of oxygen here, I need to have twice as many atoms of oxygen in my products, and so I'm going to add this coefficient of 2. I'm then going to go and say, uh-oh, look what just happened to magnesium, and I'm going to put a 2 here. When there is no number in the box, it is assumed to be a 1. So balancing equations requires us to put in coefficients. Here's something you do not want to do. You do not want to say, oh, I'm going to write the formula of magnesium oxide. I'm going to fix it by doing this to correct my oxygens. Not valid. Now think for a moment about why that's not valid. You know that magnesium is a 2+ ion, oxygen is a 2- ion, so that's the correct formula, and this other alternate formula I wrote is not the correct formula. So we do not change subscripts. This number is called a subscript, and that is part of a substance's formula. We add coefficients that come before the substance's formula in order to balance equations. So here are 5 sample equations I'd like you to take a few minutes and see if you can add numbers to the left of each formula in order to balance these equations. Sometimes you won't need to add a number, and we'll just leave it as a 1. So why don't you take a moment, pause the video, and see what you can come up with, and then I'll show you what I came up with. In this first example, I'm going to add a 3 for the bromine and a 2 for the aluminum bromide in order to equalize the number of BRs. I now have 6 BRs on each side. And because of my adding a 2 here, I must correct my aluminum and add the 2 on the aluminum. Okay? So now I'll be quiet for a bit. You please pause, and then we'll go over the rest of these. In the second example, we just needed to put a 2 in front of the hydrogen and the water. There is a 1 assumed to be by the oxygen, and generally I won't write that 1. And here you go with the remaining. I'm not writing the 1s in. If you don't see a number, there's a 1 there. We don't generally write it. So there's a little bit of balancing practice. We'll do some more of this in class and on some homework exercises. Now I do just want to point out that when we write an equation, it doesn't necessarily mean it's a chemical change. These are 2 physical changes shown here that can be written in equation form. In the first example here, what is happening? I hope that you can see that we're going from solid to liquid, and so that represents the melting of ice. In this second example, it is the evaporation of bromine liquid. And those are both physical changes because the substance is not turning into any other substance. Generally, we don't, well, I'm not going to say we won't write these, but you'll see many more for chemical than you will for physical processes. There are several types of reactions, categories of reactions. And I'm going to talk about a few of them in this first lesson, and then we'll get to more as we encounter them throughout our studies in the course. The first one I want to talk about is synthesis. I'm sure you've heard this word before. Synthesis means putting together, pulling things together. And in every synthesis reaction, we take 2 or more substances and they create a single new substance. So this is a putting together. This first reaction represents the aluminum and bromine that I did in class the week before break. I have 2 elements, aluminum and bromine, making the compound AlBr3, aluminum bromide. In the second example, that's the one that we did in our lab, or the lab that you watched the steps on the slideshow, okay? And magnesium and oxygen created magnesium oxide. And here's another synthesis of NO2 coming together to form N2O4. Now it's a little hard to see that the last one is synthesis until you balance it. It actually is 2 of the same particles coming together. And of course, these all should be balanced to be completely finalized. So pause for a moment and balance the first 2, and then we'll check in. Here we go. Those were actually done on previous screens. So there you have it. Now these are not just synthesis equations, they are balanced synthesis equations, which is your goal. Every reaction or equation should be balanced. Another category or type of chemical reaction is decomposition. Decomposition is actually just the opposite of synthesis. In this case, a single substance will form 2 or more others. And that's what's happening in each of these. It is coincidental that all of these are making oxygen. Those are just the ones I happen to pull. So don't feel that oxygen always has to be made in this case. But pause the video and see if you can balance these as well. And there you are. So there you go, a few examples of decomposition. The last category is something called double replacement or double displacement. I tend to say double replacement, and I tend to abbreviate it as DR. What happens in a situation like this is we have pairs of compounds that are ionic, and what happens is the ions rearrange. In a schematic form, I could say that that's happening this way. I have a positive and a negative ion, AB, in one compound, a positive negative ion in a second compound. And if you think about this and rearrange, there are only two possible combinations because only ions with opposite charges will come together. And so our two possible products are AD and CB. And I write the CB as in that order because we generally put the positive piece first. So you notice the ions rearrange, but they don't change, okay? They just sit next to a different counter ion. So 2 examples given below. Let's take a look and break this down. So what I've done here is I have circled the individual ions and indicated their charges. Now some of them are simple ions that have a charge based on their location on the periodic table, and some of them are polyatomic ions like this nitrate right here. This NO3 particle is not a simple ion, it's a polyatomic ion. But you have tables of ions to use for reference, okay? And I hope those are, at this point, already in your resource folder. And if you notice what's happening, the silver here has aligned itself with the Cl right there in the products, and the magnesium here has aligned itself with the nitrate there in the products. And these subscript numbers that you notice, for instance, this one and this one, are put in because each ionic compound has to have a net charge of 0. That's a 0, by the way. Okay? Now this equation has the formulas at this point correctly written, but the equation is not balanced. And so I'm going to scan across for equality of atoms and conclude that I need to put a 2 right here, and it's a little tough to squeeze it in, a 2 right there to make that equation balance. So I needed these 2 coefficients to balance it. Why don't you pause the video and take a peek, see if you can break down the next one, possibly doing what I did above, circling and labeling charges, and then see if you can balance the equation. So here we have it with the ion charges indicated. And to balance this, we are going to need to put a 2 here and a 2 here. Okay, so that's just a little bit of an introduction into those 3 types of chemical equations.